Thank you all for joining today for Dave Goldberg's SNAPP seminar. Dave is an associate professor at Cornell. Previously, he was an associate professor at Georgia Tech. He received his PhD in 2011 from MIT. Dave has won many awards and has held many leadership positions in applied probability. He's received the Career Award, an Applied Probability Society Best Publication Award. His students have received the Nicholson competition first place, and he is an associate editor for stochastic systems, stochastic models, and previously for operations research. He's also former chair of the APS Society, and recently he has led initiatives to engage more undergraduate students in operations research and analytics research. Dave, we're excited to hear what you have to say about network revenue management and the new PTAS result. The floor is yours.
Awesome. Thanks, Daniel. Hey, everybody. It's great to see a lot of friends here. So I'll keep it kind of informal, try to make it a little fun. Let's see, I won't be closely monitoring the chat. I see Daniel put something in the chat. I'll ignore it. Okay, so today I'm going to be speaking about, as Daniel said, polynomial time approximation schemes for network revenue management when you have general correlations and long horizon. But we'll see that the tools that we introduce are actually quite general and should be broadly applicable to lots of problems in OR and applied probability when you want to introduce general forms of dependency and it's not clear how to proceed. So let's kind of get into it. Also, like, if people have questions, you just feel free to shout it out at any time. You know how I can be. So now's your chance to pay it forward. Just, no need to raise your hand, right? So, yeah, so some background. So there's been a growing interest in modeling more complex dependencies in OR problems across lots of different domains. I know several people here in the room have been thinking about such things. I'll just mention briefly, for example, in network revenue management, there's been an interesting recent line of work going beyond the case where you have kind of independence or you have strong concentration to study more general dependencies. And that's motivated by, several things, including that people want to study kind of more complex phenomena. We have much more data and more complex models now, etc. So if you want to study general dependencies, you don't want to kind of assume a specific form for the dependencies. You want to kind of let it be pretty general. That puts you in the kind of conceptual domain of kind of having a things being driven by a general stochastic process, which is going to be governed by a filtration. And to connect it to a literature that we're going to be leaning into in this talk of stochastic programming, you could kind of think about your dependencies as evolving like on a huge scenario tree, where the scenario tree can be put into correspondence with like the probability space driving the kind of complex dependencies of your model. And so, for example, you might have a high dimensional information vector, which is evolving over time, which is kind of driving the stochasticity in your model. So you could imagine, the realization of something now kind of depends on the evolution of some high dimensional complicated information process. You can have full history dependence across the whole horizon T, so kind of very general forms of distributional dependence. You could also kind of think about this as kind of a very general form of Markov modulation where you possibly have a huge number of states. Let me just, in case I don't remember if I did, let me just give a shout out. This is joint work with my PhD student, Sabri Umu-Seton. Umu, you want to give a wave to everybody? And Yulun Chen. Yulun, are you here? I don't know if Yulun's here at the moment. No. Okay, so, but of course, when you start thinking about complex dependencies and Markov modulation with huge number of states, this kind of scenario tree, which is capturing kind of how the randomness evolves, is generally going to be extremely complicated. And, it'll have size, that tree will have size exponential in the time horizon. And if you want to think about it, the dimension, where here when I use the dimension, you should think about it as the dimension of that information vector. But it is really just capturing the fact that there's a huge number of states, if you want to think about it that way. And for such problems, it's not necessarily the integrality component of some online optimization problems that's first order driving the complexity. It's the fact that this scenario tree is so huge that even if it was, you looked at the LP relaxation and you just had to solve the fractional online problem, the dependency structure is so complicated that you still, it wouldn't be clear that you could really say anything. And again, to lead into that connection to the stochastic programming community, for many problems in OR, once you kind of get rid of the integrality type of constraints there and you're looking at the online fractional problem with complex stochastic dependencies, that's really in the setting of what would be considered a multi-stage stochastic linear program. Another important point here, we don't want to assume that like the input to the problem contains this huge tree, or that the input to the problem contains like a billion state Markov chain. Instead, and as is consistent with a lot of work in that domain and in high dimensional control, we assume that you can access this kind of dependency and randomness through a conditional simulator. What is a conditional simulator? You can input any kind of randomness you've already seen, hit a button, and get a conditional trajectory of the remaining randomness. You can also just get an unconditioned trajectory too. So we want to think about accessing the randomness in that way. And of course, it's kind of allowing for a totally general dependency structure that's accessed through the simulator. Great. So because I kind of want to get into some of the proof details, because again, I do think the high-level idea could be broadly applicable to like many of the problems that people here are thinking on. Let it suffice to say now that there's a vast literature on multi-stage stochastic linear programming. There's a recent survey by George Land and Alex Shapiro. I think Alex is actually having a celebration today, if I'm not mistaken. And I'm not going to kind of go into any detail about that literature other than to say there's a lot of techniques out there for kind of studying these problems on scenario trees. There's also a lot of related work in convex optimization when you have a nested structure, because of course you can kind of think about multi-stage stochastic problems as kind of having a natural nested structure where, the time t plus, to go from t plus 1 is a subproblem of the to go from t, etc. There's of course also a vast literature in high dimensional stochastic control, and also a literature in revenue management, operations research, and kind of online algorithms, computer science. But to our understanding, none of those works actually yield what would be called a polynomial time approximation scheme for the network revenue management, even the fractional version of network revenue management. So that's the multi-stage stochastic linear program in this setting, when the time horizon is not constant. And what do we mean by PTAS here? The runtime should be polynomial in the time horizon and the number of resources for any fixed accuracy epsilon. We'll talk about exactly what kind of approximations we're going for, but for now, I guess the mindset we want is we're going to be getting additive epsilon t approximations. So in that context, we're talking about being polynomial in T and M for fixed epsilon, where the goal is to get an additive epsilon t approximation. And even more importantly, your runtime should be independent of this massive scenario tree size, the dimension, etc. So you shouldn't be kind of actually touching that scenario tree. The goal is to kind of try to cleverly use that simulator in kind of a Monte Carlo way to get efficient methods that don't actually require a runtime depending on the whole scenario tree. Where I note that a lot of the literature in multi-stage stochastic linear programming by default is kind of working with the scenario tree itself and getting runtimes depending on the size of the scenario tree. Let me point out a very important reference, which is a polynomial time approximation scheme when the time horizon is fixed, which is a very different regime than we're going to be looking at by Swamy and Schmoys, who's across the hall from me. And I will note that when t is fixed, it's very natural to think about a multi-stage problem using kind of a backwards inductive logic where you say, well, let me think about what happens at the very end. Let me nest that one further, etc. The problem is when you're in this kind of high-dimensional complex dependencies regime, when you implement things that way, you effectively get conditional expectations with t levels of nesting. And even if you try to implement that very cleverly, you're still ultimately going to get kind of a runtime exponential in t. There's ways to speed that up, but you still get that t in the exponent. And that's exactly what we're trying to avoid. I will say that the results of Swamy and Schmoys are incomparable to our own because they're looking at kind of much more general parameter settings in other regards. But it's kind of a fixed t versus a large t kind of is conceptually different thing we're looking at. Let me also point out some past work of myself and co-author Yilun, which is, we recently we're working on polynomial time approximation schemes for optimal stopping, which we will notice is the same general framework. You have a simulator. You can think about optimal stopping as a multi-stage stochastic linear program where, you have to stop at least once along every path. You can phrase that as kind of a linear program. But that methodology ultimately proved to be quite limited in scope. And it was using very sensitively the fact that optimal stopping can be thought of as a massive min-cut problem, and thus its dual is a massive max flow problem, even in this complex dependency high-dimensional setting. And although Yilun's thesis did have some generalizations, for example, for multiple stopping, all those generalizations had a runtime exponential in the number of stops, because what it was really doing was kind of nesting the optimal stopping machinery we had developed into itself recursively, but it had no way to get an efficient algorithm when you were in a situation with many stops. And that's kind of exactly mapping to a special case of network revenue management, which would be kind of multiple stopping when you have many stops. And that's exactly the kind of problem we'll be dealing with today using a very different methodology than what I had studied with Yilun in the context of optimal stopping previously. So before talking about main results, any quick questions about the setup? Cool. So I'll just briefly talk about what kind of assumptions, what regime we're going to be in for network revenue management. So the general setting of network revenue management is at every time period, somebody arrives and the question is, do you make the sale or not? If you make the sale, you get a profit and they use up some amount of various resources. If you don't make the sale, you don't use the resources, you don't get the profit. So we're going to be looking at a network revenue management problem where things are kind of normalized. So everything's kind of lying in the interval 0, 1. So we assume that, if you choose to take the sale, your profit is always in the interval 0, 1. We assume there's m resources, and the amount of any given resource that a person uses is also normalized to belong to 0, 1. Although our results don't require it, you should, the general mindset we want to have is that the total amount of any given resource that we have is kind of scaling with the time horizon, and there's m resources, and in any one period, the amount of each resource that someone might use is between 0 and 1. L is going to represent the maximum number of positive components that anyone's resource consumption vector has. And that's going to appear in some of our complexity results. And it's a common assumption in network revenue management to have L be much smaller than the total number of resources M. And for several of our results, we will in fact hold L fixed while M is allowed to grow. We're also going to have an assumption that the positive resource usages are bounded away from zero. We're going to denote that by iota. And we're just going to make kind of a blanket assumption that any positive resource usage, you're using at least iota greater than zero. That kind of comes into play in kind of a final step of our analysis where we do a little bit of rounding. We can kind of weaken that assumption some, but it's kind of, we don't yet know how to totally remove it. We assume we have this conditional simulator, which I already referred to, that takes C units of time to use every time you use it. We assume you can sample uniform random variables, and that you can draw a random time between 1 and t in big O of 1 time, so constant time. If we were really wanted to be particular, we might say drawing a random time between 1 and t takes like log t time. We're just going to say that these kind of simple primitives take constant time. We're also not going to stress about reading and writing numbers. We'll just assume all those kinds of things take a single unit of time, big O of 1 time. Great. So with that, let me jump into the main results. So the first result is a polynomial time approximation scheme for the network revenue management multi-stage stochastic linear program, which means specifically a polynomial time approximation scheme for the fractional network revenue management problem, where we can implement a randomized policy pi on any given omega that you give me. So I can implement a policy pi online such that that policy's performance is within epsilon t of optimal in expectation. And the runtime is, we have that C from the simulator. And then you can think about it, it's like whichever smaller m squared and t, the plus 1 is just for the case m equals 1. So kind of whichever smaller m squared and t, and what's in the exponent there, L squared, where L is again the upper bound on how many positive components we can have, iota to the negative second. So again, iota is this kind of constant lower bound on any non-zero resource consumption, and an epsilon to the -4. Now that's of course not like a super fast kind of polynomial runtime, but for any fixed L, iota, and epsilon, it is polynomial in M and T. And one thing that's really interesting is that if the number of resources is constant, then that number, because if T is large, then if M is small, that's going to be dominated by M. And of course, if M is small, then L is small because L is at most M. When M is small, we find that the algorithm we're going to talk about here actually has a constant complexity for every decision, which is a little surprising because it's this like complicated high dimensional long horizon control problem. And we're actually going to get that you can kind of make each fractional decision in constant time when the number of resources is small. And let me also point out that if instead of actually computing and implementing a policy, we just wanted to know the optimal value approximated in the same way, we can replace epsilon -4 with epsilon -2. The extra epsilon -2 comes from a penalty term that we need to be able to actually implement a policy. Let me point out that the methods we're going to talk about are...
Can I ask you a quick question?
Yes, of course.
Is M the budget of resources or the types of resources?
Sorry, M is the number of resources.
Resource types, or the how much you actually have.
No. There's no reference here to the actual right-hand side. M is like how many different resources you have.
Okay. Thanks.
Well, in some sense, iota -1 is the resource budget in a way.
Say it again.
Is 1 over iota in some sense the budget per resource?
No. The budget per resource we should think about is scaling with T. Iota minus, I mean, like, what this says is that the mindset we want is that the amount of each resource I have is roughly going to be a constant times T. That constant doesn't appear here. Iota is to do with what happens in any one period. So that says that if I use a positive amount of a resource in any one period, I use at least iota of that resource. So for something like multiple stopping, where we want to think about the setting where maybe the total number of stops I give you is like t over 8 or something like that. Iota is just 1 and it's not relevant. It just turns out that for the method we do, we ultimately relax the constraints, and then to recover a feasible solution, if you're requesting strictly positive, but very, very small amounts of a resource in any one period, it can be hard to remap it back to how much profit that's costing you in some sense.
Makes sense.
I'll come back to that at the end. But the way to think about it is the right-hand sides, which don't appear in the complexity bound, are kind of big scaling with t. Iota is just to do with in any one period. And if things are just 0, 1, then iota is just 1 and it's not me. Great. So I'll leave it at that. Other questions? Great questions. Okay. And I'll point out that the subgradient descent approach that we take is quite different from the approach that Yulun and I took in optimal stopping, which was, again, ultimately based on flows. This is a much more general methodology, which we think could be broadly applicable to many kind of online problems in OR that people are looking at. Okay, so that was for the fractional version. What about for the integer version? So here we're gonna talk about how are we going to use that methodology to get approximation algorithms for the real network revenue management problem, which is you need to make a 0-1 decision about make the sale or not at each time period, along with 2 online combinatorial optimization problems, one bipartite max weight independent set, where in every period a node's weight is revealed and you need to decide whether to take that node or not, as well as bipartite maximum matching, where in every period a new node comes, its edges are revealed, and you need to decide which, if any, of those edges to take. And again, in all of these problems, we're talking complex dependencies. In bipartite max weight independent set, we're talking complex dependencies between the weights of the nodes, which are revealed over time. In maximum matching, we're talking complex dependencies about which edges will be present, where again, those edges are revealed online over time. At the end of the talk, I'll if we have time, I'll make those models much more precise. So as long as the number of constraints is little o of t, then our previous result, pretty much by combining with very naive rounding, yields a similar guarantee for the real network revenue management problem, which again inherits that property that the per decision runtime is just a constant when the number of resources you have is big O of 1. Maybe to make a point about one way to think about the high dimensionality is that although the number of resources is big O of 1, kind of the high dimensionality is corresponding roughly to the number of types, which may have very complex dependencies. That's going to be extremely large. It's just the number of resources is fixed when we talk about M being big O of 1. And similarly for online bipartite max weight independent set, when the maximum degree of the graph is a constant, we'll call it delta, then we get a similar type of additive epsilon t approximation to the optimal. Although there we'll need a more clever rounding scheme, because if you use naive rounding, you of course won't get an independent set. We'll talk about that at the end. And they're the weights of general correlations. For maximum matching, we get a 0.652 approximation, which we'll note is strictly greater than 1 minus 1 over e. We do require there that for the graph that's revealed, the number of edges is on the same order as the number of nodes. That could be because it's bounded degree in some sense, or that doesn't require bounded degree, but we do require that for the methodology to work. Again, which edges are present have general correlations. I'll note that the fact that 0.652 is the number there and how you do the rounding, that's coming in a black box way from recent work of Noor et al., which studies an interesting, if I give you a fractional bipartite matching one at a time online, can you online round it to an integer matching without losing too much? So they did a big part of the heavy lifting for matchings for us, and we're just kind of importing that, combining it with our ability to online derive a fractional matching, essentially. And that falls within this general framework of philosopher inequalities, as they're called, because although here it's not for a model where you have independence, it's for a model where you have general correlations, because we're studying these kind of complex stochastic dependencies, but we're comparing to the online optimal. So when we talk about polynomial time additive epsilon t approximation, it's to the optimal for the stochastic problem, not to the offline optimal. When you have complex dependencies, you can't hope to do well with respect to the offline optimal in a sense that I won't go into depth here, but you can show that. So let me pause before I kind of talk about the general methodology, which again, I think could be of broader applicability, and take any questions just about the kind of statement of results. Okay. So then I guess first, I'll make the model a little more precise in the context of network revenue management. So we're in discrete time. So when we think about there being t periods, we kind of want to think about t being large. We'll think about you have a filtration generated by some kind of potentially high dimensional non-Markovian information process, which is going to drive the dependencies. And that can contain kind of all the past information, et cetera. So it's just kind of a natural way to talk about general dependencies. In every period little t, a potential customer arrives, where that's just a modeling simplicity. If you want to think about having non-arrivals, you can zero things out, so it's without loss of generality. If you make the sale at time t, you get a profit zt, which is a function of the trajectory of that information process up to that time. I use the bracket notation to denote all the information y1 through yt. And you will use a sub it of yt of resource I for I equals 1 through m. So this is just, it's just indicating that the profit and how much you use of each resource is a function of this complicated information process up to the present time. We assume you know the time horizon and you know the budgets. We could allow those to be stochastic, but we won't here. And importantly, xt is going to equal 1 if you make the sale on that trajectory of the information process up to time little t, and 0 otherwise. So let's give a useful, and this is a formulation that we'll be leaning into, again, because of the connection to multi-stage stochastic linear programming. Let's think about this in what I'll call scenario tree world, where here, this is essentially capturing the probability space governing our information process. So each root to leaf path is kind of representing an omega, governing how our information process evolves, where we should think about like the third edge down as like a possible realization of the first 3 information vectors. The fact that it's binary here is just for convenience of illustrating. In general, the degree is going to be massive, representing kind of all the different possible things that might come for the next information vector. But it's still a useful kind of way to think about it. So since we're associating every path of the scenario tree with kind of a possible omega for your information process, we'll use the notation mu of p to denote mu of the corresponding omega on the scenario tree. Importantly, we're going to be thinking about an edge E as a partial history. So like that would be the information process up to time 3, for example. Associated with any edge, we should think about the edge as like all the information on the things until you get to that edge and including that edge. That edge is associated with a profit and consumptions of the different resources. We'll denote by mu of E the probability of that partial history. So mu of omega is the probability of like an entire path. Mu of E is going to be like, what's the probability that you get to those first 3 information vectors? And what's the kind of way to think about the policy problem Well, when we think about a scenario tree, the policy problem is asking you to assign an x of e to every possible e of this scenario tree, because that's like, that then tells you, well, at any given time period, you're facing a partial history corresponding to some edge of the scenario tree, and I need to know what should I do on that edge. And so the policy problem, when you think about it in this kind of stochastic programming scenario tree way, is it's asking you to assign an x value, which is, I've just written x here, but they're really x of e, to every edge of the scenario tree. And there's a lot of x's, which is, again, in that stochastic programming literature, they've thought a lot about how do we kind of assign all these x's, etc. And a big part of this work is we're going to question that assumption that you have to assign an edge to each, you have to assign each edge an x value. Because if we think about the problem we're facing here, that's not really true. What is online optimization? You're actually just going to get one path drawn from the distribution mu, and you're going to have to assign the x's on that one path. You're going to have to implement your policy on that one path. That means that ultimately, you don't care about assigning most of these x's. You just have to, in an online way, assign the x's along the one path you actually see. And that's kind of what's going to save us here and allow us to devise polynomial time algorithms. So let's kind of write this, let's write the whole big scenario tree problem down as like a big linear program. So we're maximizing a linear function over the x of e's. Where's that objective coming from? Well, mu of e, that's like the probability that on the path you show me, I ever get to that edge. And then if I get to that edge, what do I get? I get the profit for that edge times the x determining whether I actually make the sale on that edge or not. Subject to, for every possible path I might see on the scenario tree, I have to satisfy the resource constraint for every resource I. And the x's have to belong to 0, 1. So again, it's if you're not parsing the exact details, you could just take it at that level of understanding. You're not really missing anything. It's a massive deterministic integer program. And again, the size will in general be exponential in the horizon. And if you want to think about it, the dimension of the information process, etc. So it's like, it's too big to solve, although it is kind of what a lot of thought in the multi-stage stochastic programming community has gone into thinking about. So, okay, so now we're going to talk about, I'm going to try to convey the main idea of our approach. Daniel, when do I kind of have till, since we started a little late?
I would say 12:30, but personally, I'm staying longer. If I'm staying as long as you're talking, really.
Okay, I mean, I'll leave time for questions and stuff. So let me try to get to the main intuition, and I'll try to keep it in a easy as possible to understand manner. And please ask questions if people have any questions, because the core idea is actually really simple. It's just combining some things in a particular way and interpreting it the right way. So if people have questions, then please ask. Let me actually, maybe before I jump into that, because I know some people, a lot of people are not used to thinking about dependencies in terms of like a scenario tree. Let me pause and just give another opportunity for any questions just about how we framed it, or how I'm asking people to think about it, or the general setup, etc.
All right, I have a basic question about the setup.
Yeah.
Is there any, so obviously the decisions that lead to X depend on Y. Is there any dependence the other way? Like, or is the Y,
No, yeah, you shouldn't.
Yeah.
X is, this is like, like when you're teaching like on a probability space, X is going to be a measurable function of Y. So it's
Good.
You're assigning.
There's
no, X is, yeah.
There's no feedback where the people who arrive depend.
No, we're not allowing the noise is exogenous here. So maybe that's, yes. So that's, there are, of course, and indeed, there's critical questions as to, can the philosophy we take here extend to questions where the noise is not exogenous. And, you know, I'd say we don't have a great answer there. It is true, and some recent works have pointed this out, that every problem can be kind of put in an exogenous framework, but it's not, you kind of maybe get some change of measury things there that would make it not exactly what one thinks. And so I will also say another setting where it's actually quite interesting to ask whether this can be extended. So here we're thinking about filtrations where you have no control over what information you're getting in any given time period. You know, as you know better than most, there's of course many interesting problems where you do have some authority over this matter. And there it's actually quite interesting broadly. How do you take techniques that maybe work when you have a filtration that just evolves? And what can you say about problems where your actions determine what information you're getting? But that's beyond scope, I guess, but awesome. Okay, so here's this problem, this like huge linear program that's, well, maybe actually let me just spend 1 minute and just give kind of what's like gonna be the really high level. So pretty much we're going to take the integer program, relax it to a linear program. We're gonna use a penalty method and throw the constraints up in the objective and just penalize your expected deviation of the resource constraints. We're gonna define a subgradient method for that penalized problem and observe that it's so simple and structured that you can actually implement it efficiently and online in polynomial time. And then you can kind of map it back using some kind of rounding. That's pretty much it. That's like, so that's I'd say the high level of it. I'm now going to dig into some more depth to make some of that more precise, but that's kind of where we're going. And what the big picture takeaway is that you can actually implement for some interesting online problems subgradient methods efficiently on the fly, where you're not computing most of those X values. You're just kind of computing them for the path you care about, and you're doing it cleverly, and you're doing it online. That's the punchline. But let me proceed. So and make some of that more precise. So, okay, so this is kind of the original network revenue management problem we started with. We're going to relax it. We're, again, when T is long in the setting we're in, at least for network revenue management, rounding back to an integer thing is not like the hard part exactly for this regime. For other regimes, it is more interesting. Here, where the real challenge is going to be in solving the LP, this big online fractional problem. Okay, so we're going to define a term that we call penalty, which for each resource I, path P, and whatever big solution X you're currently thinking about, is just going to be varphi there is just a constant. We're going to make it 1 over epsilon. It's going to be the penalty multiplier. And the rest of that expression is just how much you violate that resource constraint on that path. And that's going to allow us to write a penalized version of the problem, where in the objective, we actually have, summed over all constraints. What is your expected resource constraint violation? We call it penalty just so we don't have to keep writing out certain expressions. It's just the obvious way to take the constraints and you put it into a penalty formulation where you're penalizing your expected deviation of the expected violation of the constraint. Let me point out that we're not replacing like each individual term within the expectation by its own expectation. So it's still this kind of non-trivial high dimensional thing. But we've simplified things a lot by putting it in the objective.
So phi here is a constant, right?
Yep. Phi here, we're just going to make 1 over epsilon. That's not like a function of that.
Yeah, it might look like a function as well. So
yeah, I understand. Yep. It's just we're going to make it 1 over epsilon. Yeah. Great. Okay. So now I'm going to, I claim that if we want to think about taking a subgradient of this penalty objective, it's actually really easy to understand. we're going to define an additional term. So we have penalty. We're going to define additional term we're going to call violated, which is just the same multiplier, which is going to be 1 over epsilon times not the amount you violate the inequality, but just the indicator for whether on that path for the solution X you're at, you violate resource I's inequality. It's just the indicator, which comes up naturally in the subgradient. So we recall that penalty is just the amount you violate. And then it just follows from basic subgradient kind of logic that if you want to take the subgradient of that penalty up there, which is, again, that's like how much you violate, it's just the indicator. Okay, what do I mean subgradient sub x of e? Again, it's not important that you understand kind of every detail. We want to think at a high level, we're optimizing over the x's. So what I'm talking about now is suppose you take a subgradient of the objective, where again, the variables are the x's, and look at like x of e's, what is the value of x of e in the subgradient? Like if you look at the subgradient as a big vector. And the point is, just by basic subgradient logic, it's going to be the indicator that e belongs to the path, because if e is not in the path that you're looking at the penalty of, then e does not arise in the logic, and it'll just be zeroed out, times the coefficient of edge e in that kind of particular inequality, that like just again by basic subgradient logic. And then again by basic subgradient logic, you just get times the indicator that the violation was actually non-zero. And that's just like, so it's that simple. And so then if we look at the objective now, we see that, well, the objective, we weren't just taking the subgradient of penalty. We need to take the subgradient is the sum over m of the sum over p, mu of p times penalty. But it turns out this is so simple that, like, if we do that, we get pretty much the same thing, except now we're summing over all the paths. Well, okay, let me, so maybe ignore the z of e minus for now. I'll talk about that at the end. Let's just think about what is this sum over m, sum over p through e, mu of p over mu of e, a times violated. So, right, I said the subgradient is like indicator e and p times the coefficient for e, ai of e times violated. But now if I look at the actual objective, I'm summing that over the resources, I'm summing it over the paths, and I'm weighting it by mu of p. And so I'm just doing here, it's just the same exact thing. I multiply and divide by mu of e because that's going to allow us to interpret that as a conditional probability, which is going to be, or a conditional expectation, which is going to be very helpful. And instead of writing indicator e and p explicitly, I'm just summing over the paths through e because everything else is zeroed out. But the point is that the logic of how you take a subgradient of the hard part of the objective is actually extremely simple. You can look at the subgradient of just that one penalty term, which is straightforward, and then sum over the resources, the paths, and weight by mu. And again, if you multiply and divide by that probability of that edge, on the next slide, I'll spell it out that that term actually has kind of a very nice conditional probability interpretation. What about that first term? Well, the first part of the objective is just a very straightforward linear thing. And what's the coefficient of x of e? It's just mu of e z of e. And again, since I said I'm factoring out mu of e, that's why we get just a z of e. So what's the right way to interpret this? Well,
You're off.
Oh, a question. Rhonda, please.
Sorry.
Yeah. She was just unmuted.
Oh, I see. So what's the right way to interpret this? Well, the subgradient of the objective evaluated on kind of edge e, it's just z of e, the profit associated with that e, minus this constant penalty, which we're going to be set to 1 over epsilon, times essentially a sum over all the resources of the conditional probability that you violate the inequality for that resource, given kind of the edge you're on, so given what you've seen so far, and you weight by the coefficient of e coming from that inequality. And that's pretty much it. And it has this kind of simple conditional probability way to think about it. And again, I have factored out a mu of e. but you don't really have to worry about that. What you have to worry about is it's simple linear term minus weighted sum of conditional probabilities, where those weights are just like very straightforward coefficients. And again, keep in mind when L is small, most of these things will be zero because A sub I of E is only positive for at most L. So it's kind of a sum of a few conditional probabilities conditioned on what you've seen so far up to that edge E. So that makes it really easy to come up with a stochastic subgradient. We're just gonna, to get a stochastic subgradient, we're just gonna sample a single trajectory conditioned on that history and take the indicator for whether we violate inequality I on that one path. That's just a natural way to get a stochastic subgradient whose expected value will be this conditional probability. And that gives us a very simple stochastic subgradient where it's just the probability of that edge times the linear coefficient for that edge minus the sum over all resources, or essentially minus a weighted sum of just the indicator. Do you violate the resource inequality on this one random path that we drew through your edge, because it's conditioned on being up to where you are. But it's super simple. It's just you draw a random path conditioned on being there, and you're kind of just taking a weighted sum of these indicators, and it's your profit minus that weighted sum. And that term, it's a noisy proxy for like, how much are the paths through you tending to violate the resource constraint? So it's kind of a natural thing. And of course, the conditional simulator allows us to do that sampling very easily. Questions about that? Okay. So we can then think about implementing like a massive stochastic subgradient method where we start at 0. We actually run like, you can think about running subgradient descent or stochastic subgradient descent. So we're actually doing simple stochastic subgradient updates using that logic from before. P hat E is like that random path through E that we use to get the stochastic subgradients. The superscript K there is just because at each step, we want to redraw that path independently for each edge. And it turns out, don't worry about the parameters here, that if you set the parameters in a reasonable way, and you were to solve that massive stochastic subgradient method on the scenario tree, which we're not going to do, it's just kind of a thought experiment. If you were to do that, then after kind of epsilon to the -4 iterations, with the appropriate step sizes, the average iterate would be within epsilon t of optimal and expected revenue, and it would have kind of the expected total amount you violate all the constraints would be at most epsilon t also, which is good for rounding and kind of patching the infeasibility, doing some naive thing. And I'll note that for fixed epsilon and L, the number of iterations you need here, which is going to be kind of L squared epsilon to the -4th, is just going to be a constant independent of t. So that's great. The problem is there's too many E's. We can't implement this method because, like we already said, we can't touch the whole scenario tree. It's too darn big. So let's think again about what problem we are really solving. So, right, we're not really solving this problem. We just need to solve for the x's on the path that's revealed to us. We have to solve for x of e along this one path, which is revealed to us online. And so we really only need to compute this kind of average iterate coming from our stochastic subgradient method for t different values of e. That's not 100% true, as I'll explain on the next slide, but that's kind of conceptually the way we want to think about it. Well, let's think about computing the kth iterate on edge E for a single E, which is on the path that we were actually given. So, you gave me, we're online. I tell you, okay, this is the edge we're on now. What is the value of your policy on this edge? Well, let's think about just trying to implement one step of the stochastic subgradient method to give us the value of this edge? Well, to implement the stochastic subgradient method and determine like the value of the kth iteration on this edge, what do I need to know? Well, I have to be able to do the subgradient step. But to do that, I need to know, well, I need the k minus first iteration on that same edge. And I need the indicator along that random kind of condition path of whether I violate the inequalities for the x from the previous iteration, for xk minus 1. And these are the things that I need. Okay, but how many different values of xk minus 1 actually appear here? Well, I've got xk minus 1 for the edge I'm on, and I've got xk minus 1 along that one random condition path that I used to determine the stochastic subgradient. If I had that, I could just plug it into the indicator and then plug it back into the gradient step and get what I want. So again, all I need is the k minus first iterate values for the edge I'm on and all the edges on this one random path that I drew conditionally through the edge that I'm on. But that's only t different values. And so to compute, right, we started, I want to compute what is the output of my big stochastic subgradient method after k iterations on this edge. But what we've just discovered is that to do that, I only need to know in that same big subgradient method, what were the k minus first iteration values on t different e primes. I don't need to know it for the whole tree. And then it's actually very straightforward if you had those values to combine them to actually implement the gradient step. But now we can simply apply this recursively. So if I want to know what is kind of the value from the kth iteration of that big stochastic subgradient on the edge that I'm on, well, I can relate that to some kind of small amount of work, plus I need t additional values from that big tree evaluated on iteration k minus 1. But of course, I can recurse that because to get each of those t values on the k minus first iteration, I will be drawing random paths through those, and I will need t values on the k minus second iteration for each of those t things. You're just getting like a t squared, t cubed, etc. And since we're taking the penalizer to be epsilon to the minus 1, if you put it all together, that actually gets us a polynomial time method for determining the fractional value output by our massive stochastic subgradient method on any one edge. Because we took a minimalist approach and said, if I look carefully at the stochastic subgradient methods, what other values for which iterations on the tree do I actually need? And when we just did that in kind of a straightforward and logical way, we saw that since we're only going to a constant level of depth, and at each kind of recursive depth, you only needed t further values at the one kind of, iteration complexity less, that kind of when we put that together, we got a polynomial time complexity. And we're only computing for any given kind of iteration depth, the values that we really need. And the other great thing is this can be implemented online when you see E. You don't need to know the future, right? An edge E comes up. All you need to do is take that, you draw that conditional sample path. It may not reflect what real future you see, doesn't matter. And then for every edge on that one conditional sample path I drew, I'm going to take conditional sample paths through them. But it's all using the simulator. I don't actually need to know the future to do it. It's actually a depth. So it can be implemented online. And pretty much that's what gives us the polynomial time method for implementing this online fractional solution. And then when you combine with naive randomized rounding and you got to clean up the infeasibility, but you can just do that in a very simple way, you get the main result. Let me actually now point out, so here we have a polynomial in T, but that logic doesn't recover the constant complexity when M is small. Let me quickly talk about how to do that, and then maybe I'll wrap it up. Let's go back to thinking about how we were computing the value from the kth iteration of our subgradient method on a single edge on the path that we were given. Well, as we already pointed out, you need to compute the kind of k minus first iteration on that edge and the k minus first iterations on the edges along this kind of random path pad. But we don't really need the k minus first iterations for every edge on that path. I just kind of need to know, is it true that the sum of AIX along that path was at least B? But you can use sampling to approximate that sum. And you can, in fact, just sample a constant number of time periods to approximate that sum, and then you multiply it by t. Okay, that's like really simple. Of course, there's like an indicator which is discontinuous, which is kind of a stinker. So there's a problem with that logic. Otherwise, that would be the whole thing that you would do to get the recursive complexity down from t to the something to essentially constant to the something. It's just we're going to subsample and just compute that kind of indicator this, at least that approximately, by just sampling a few edges along that path and using, Hofting's inequality or something. So pretty much we're going to fix that by redoing all the steps. I'm not going to go into those details here with a smooth penalty. You need to smooth out the original kind of penalty function so that kind of the subgradients are smoother, and then you can just do the sampling and it's fine. One simple way to smooth it out is instead of having the penalty be the amount that you actually violate the inequality, we make it the expected amount that you violate a perturbed version of the inequality, where you need to we perturb it by a uniform with specially chosen parameters. You don't need to worry about y is at epsilon squared t over m. It turns out that gets you kind of the right kind of scaling. But the point is, when m is small, we're actually perturbing each resource inequality in the penalty by a random amount that scales with t. It's like some kind of epsilon squared t, but we're really noising it up so that we can actually only sample kind of very sparsely and get away with it. It turns out if you put that all together, and especially since we only wanted an epsilon t approximation, it can all be made to work when you put it all together. If we were not content with an epsilon t additive approximation, we would be out of luck. It turns out because that's all we want, when we put it together, we're okay. I won't bother you with exactly what that constant number of samplings looks like. Let me skip over that. Let me comment very, very quickly on independent set and matching. So for independent set, let's consider a simple setting where you have a known graph, a known bipartite graph with t nodes, but unknown random weights, which are revealed one at a time. And you have to decide whether a node's in or out when its weight is revealed. And you need an independent set with probability 1. The weights can have general correlations. The max degree delta now plays the role of L. And of course, your constraints are like x of this edge of the scenario tree plus x of this other edge of the scenario tree has to be less than or equal to 1. Those are the independent set kind of constraints. So pretty much we're going to use the same algorithm as before. The runtime now looks like delta to the delta epsilon to the negative fourth. That doesn't matter too much. That gets us a good fractional solution. But how do we round it? It turns out there's a really simple dependent rounding scheme that works here. It's like, you generate a single uniform 0, 1. You take a node in the left partite if it's greater than that uniform. You take a node in the right partite if it's greater than 1 minus that uniform. Why is that kind of a reasonable thing to do? Because, well, if this one's greater than u and this one's greater than 1 minus u, then added together, they're going to be greater than 1, which is kind of like, if you solved your fractional problem right, that shouldn't really be happening with meaningful probability. There's a little bit of a patch up where, because we have these some amount of violation, your fractional solution, when you do this rounding, could tell you to take someone whose neighbor you've already taken. You just make sure not to do that, and you're fine. If your fractional solution was actually fractionally feasible, it turns out this would be lossless rounding. It actually relates to some old work about rounding fractional cuts. And one interesting thing here is that for bipartite max weight independent set, the scenario tree problem is actually totally unimodular. If you think about that big IP, it is totally unimodular. That's a concept, kind of stochastic totally unimodularity that's actually been studied in some other communities. And that follows from the fact that, like, even in that really big problem, you only have a constraint between an edge at an even depth of the scenario tree with an edge at the odd depth of the scenario tree. So in some sense, there's lossless rounding there. Let me not dig into the matchings. Let me just say that it works pretty much exactly the same as before. And we combine with the recent work of Noor et al. And implement their rounding scheme to turn our fractional solution into an integer solution, which is a 0.652 op. Let me quickly jump to talking about some future research in open problems. Of course, like e to the epsilon minus 4 is not practical even when m is small, but we have not pushed the frontier of convex optimization methods here, looking into acceleration, looking into primal dual methods. There's also a lot of interesting question about doing smarter rounding here. I know there's been some work in that space in network revenue management, but it seems there's a lot that's not yet understood. There's also some interesting implementation details, and people have been putting in a lot of thought about solving massive LPs, using GPUs, et cetera. So it's interesting to think about connections there. This method should be pretty broadly applicable anytime you can relax something to like a large stochastic convex program. You should probably be able to implement something like this and use a subgradient method on the fly. So it's interesting to think about what other settings this could be interesting for. It's also like, it's not entirely clear to us how this relates to like, there's tons of different methods in stochastic optimization where this should have connections to it. So that's something cool. Thinking about complexity implications in the same way that that result of Swamy and Schmoy's I referenced originally, that actually has had quite a few complexity implications. So if we take this result as like a black box, you can think about what that means. Just combining thinking about online algorithms with thinking about this scenario tree stochastic programming way to think about the world. It seems like there's a lot of unexplored synergies there. Like I pointed out that notion of total unimodularity of the like scenario tree problem. It just don't seem that explored in the ORCS kind of community. You could also think about trying to use, because these are hard high dimensional problems, use some of the outputs of the algorithm to help guide kind of ADP or deep learning methods. Very briefly, there's some really fascinating questions here about lower bounds also. Trade-offs between the different parameters here. What if I allow you some dependence on the size of the scenario tree? Or like you can be a little worse than polynomial in T, et cetera. What does that mean? How does it relate to the recursive depth that you want to go out here? Another interesting thing here is, right, I teed it up as like you only have to solve for that one omega you're given. But of course, you might really be getting, ultimately you're going to have to solve the online problem many times. How would you think about that in a complexity setting? And this one is, I think, like I'll leave people with this kind of what I think is a profound philosophical question. For all these like, Monte Carlo kind of high dimensional control methods where it's assumed you have access to some kind of simulator, like what does that mean? And where is the simulator, where is it coming from? Like, how do we want to think about the complexity jointly between building a complex simulator for a high dimensional problem and like the complexity of the algorithm you're going to run with it? Like, how do we want to think about that? And I think that relates to, of course, established notions like VC dimension, which there's been some quite interesting work on recently at the intersection of OR. But also, I think there's new notions of complexity that are going to be needed there, related also to recursive depth that you go out to, related to dependence on scenario tree, et cetera. And with that, I'll wrap it up.
Proceed.
Happy to take any
CIV.
questions.
Thank you.
Thank you.
Thank you, Dave. For people that are still around, I think we can take a little bit of time for questions. I would have one. What did you use about the structure of the NIM problem that is fundamental to the NIM problem? So, for example, just out of curiosity, my work with Sid was sort of saying, hey, these O of 1 regret guarantees, you can get them for NIM. You can actually also get them for online stochastic bin packing. is there much in here that would clearly not generalize to other online decision-making problems?
We think it should completely generalize in the same way that your work with SID or some of these other paradigms have, definitely. It's just an illustrative. These were just 3 kind of illustrative examples, but indeed.
Cool.
Thank you.
We have other questions? All right, then thank you, Dave.
Thanks a lot, everybody.
Always a pleasure to see you. And
Cool.
We will look forward to our next talk 2 weeks from today.
Bye, everybody.